Many times we want to use a synthetic key that is surrogate key as primary key column in our table. There are many advantages in using such key, and synthetic key is just a sequence of numbers. And we will now create such column in our Monet database. So I will go here to terminal, and I will first run this code here. This will create a new table. What is special for this table is that it has this column, serial column, that is of type serial. And serial is actually an integer. It has the same range as an integer, but serial is a more complex data type because we will use this data type to create a synthetic key. I will now enter one row in our table, and for that I only have to provide values for other columns. I don't have to provide a value for serial column, just for the name column. But if I run this code, and if I then read from our table, I will see that I have a value in the serial column, and that value is 1. And if I repeat this process 2 more times, for example, I will run this code here now, and then if I read from this table, I will see that now I have 3 values. So I have values 1, 2, and 3. And besides using this serial data type, it is also possible to use big serial data type. The difference is that serial is integer and big serial is big integer, but everything else is the same. Now, when we have entered this new row, Monet somehow know what other number to provide. And that means that Monet is remembering what was the last number that was used, and that information is saved in a database object that is called a sequence. And we can read about those sequences from one system table. That table is sys sequences, and this is that table. And here we can see our sequence that is created when we have created a column of serial data type. This is the name of our sequence. Now, we said that serial data type is integer, and that we can also use a big serial data type that should be big integer, but we have one more syntax, and this is that syntax. So we will create another table, but this time we are using this auto increment syntax to create a synthetic key. This time we also have ability to define what kind of integer to use. So we can use tiny integer, small integer, any other kind of integer. So I will create a new table, and then again we will read from our system table, and there we will see that we have now 2 sequences. So we have created another sequence, and this other sequence is of type small integer. And if I try to enter a value in this column, I will get an overflow because my value is 33,000, and that is too big number for small integer. We can also notice here that inside of our auto number column, we can enter a value. We don't have to rely on that automatic system that will place some value inside of our column, but we can provide our own value. Now, sometimes we want to know what will be the next value for auto increment column. And for that, we have this expression here. So we will read the next value for this sequence. Now, why would we do this? Well, sometimes we want to know a value in advance because we want to write that value in 2 places. We want to write this next number in primary key column in one table, but we also want to use this same number to be written in other table as a foreign key. So if I run this statement, we would see that next value for this sequence that we have just created, this of type small integer, will be 1. That is, this will be the first value. I will now clean my screen. We have saw earlier that it is possible to write our own number inside of synthetic key column. But if we try to do that in serial column, that is of type serial, this will fail because we know that inside of this column we already have values 1, 2, and 3, but now we are trying to enter a value 1. And this will fail because of primary key constraint violation. When we create a column of the types serial or big serial, such columns will automatically get a primary key constraint and not null constraint. So it will not be possible to enter same value 2 times. But such limitation is not valid for synthetic key columns that are created with auto-increment syntax. So in that case, it will be possible to enter a value 1, although we know that this column here already have a value 1. So I will now enter this value, and then I will read from this table. And in this case, we have 2 ones, and this is allowed for auto-increment columns, but it is not allowed for serial and big serial columns. Now, it would be great if we would have an ability to prohibit user from entering their own values. All of the values for synthetic key should be automatically created, and there is syntax for that. So I will now create another table, but I must say that this syntax will not work in Monet database. This syntax maybe works in other databases, but not here. So syntax is like this. First, we define the type of integer. It could be integer, small integer, or anything like that. And then we write generated always as entity. So this means that automatic system should be always used. So I will create this table, and then I will write some value inside of this table, and we will see that this will not fail. So this will work. I can read from this table, and unfortunately this syntax is not working in Monet database. I will now clear my screen. We said earlier that syntax generated always as identity will fail to prohibit users from entering their own values. But this syntax is still useful, and it is useful for defining our own custom attributes for a sequence. So we can run a code like this. We are using this syntax generated always as identity, but after it, inside the parentheses, we can define our values for sequence attributes. So we have this parameter, we have min value, max value, we have cache, and we have cycle. So if we now read from our system table, syssequence, we will see those custom values for attributes. Now we have just created this sequence here. Start value is 8, that is this 8. We have minimum value 7, maximum value 20. We can see them here. So we can define our own value. And if we now start to use this table, if we enter some row inside of this table, we will see that the first key is 8. That is because this parameter is 8. Start means the first value. And then if we create another row inside of this table, this one, in this case, the key will be 10 because increment is 2. So every new step will increase this number by 2. Now, if we go back to this page, we can see something about our attributes. We can see that our sequence will loop between minimum value and maximum value, but it will start with this attribute, with start with number. It will start from this, and this start with number should be somewhere between minimum value and maximum value. Now, we don't have to provide these values. We don't have to provide start with minimum value and max value. We can just say no min value and no max value. In that case, we would use some default values. Now, increment by is important attribute because it will define whether our sequence is ascending. If increment is positive, then our sequence is ascending. So we will have number 1, 2, 3, and so on. But if it is negative, then we have the descending sequence. We are going then from bigger numbers to smaller numbers. We can also cache our values. If we cache our values, that will speed up a database, but in the case of failure, these numbers will be irreversibly lost. And so we can say no cache. In that case, no numbers will be lost, even in the case of the system failure. And we can also define attribute cycle and no cycle. Cycle means that we will go from minimum value to maximum value, and then we will start again from minimum value. So we can go through that range several times during time. But if we use no cycle. In that case, when you reach the upper or lower limit, depending whether we are using ascending or descending sequence, an error will be raised because there will be no more values to use. Let's go now back to terminal. I will clear the screen. We saw earlier that if we use syntax generated always as identity, we can provide a custom values for sequence attributes. But we were not able to give a custom name to our sequence, so this time we will use something different. First, we will create a sequence. So we will use the statement create sequence. We will create sequence like this one. We will give it a unique name. We will define a data type, and we will define all of the other attributes. If we now read from our system table, we will see a new line for this new sequence. And here is our new sequence. And now we have to tie this sequence to a column. And for that, we will create a new table. So we have a create table statement. We are creating a column, sequence column of small integer data type. And we will use default constraint to tie our new sequence to our column. So by using a default constraint, our sequence will provide the values to our column. So we have created a new table. And it is also possible to alter our sequence. For that, we have alter sequence statement like this one. It is similar to create sequence. The difference is that now instead of using start with, we are using restart with, and everything else is the same. We can also change the data type of our sequence, because internally Monet will use big integer no matter what kind of data type we choose here. So we're still able to change data type, but we are only changing the range in which sequence will operate. And at the end, we can now see our changes by using this statement. We can read from our system table. We will see that now values have changed. Instead of 10 and 7, we now have 21 and 15. And at the end, we can delete our sequence. For that, we have this statement drop sequence. And this statement will not work because this sequence is used inside of our table. So first, we have to remove usage of that sequence in our table. I will just delete the whole table. So drop table sequence object. So I will delete the table. And then again, I will try a drop sequence. And this time it will work. So this is how we can delete our sequence. I will now clean my screen. If we want to know what number will be generated by our sequence next, we can use a function with the name getValue4. And this function will accept two arguments. First argument is the name of a schema, and second argument is the name of a sequence. So if we run this, we would get, for example, 13. If we run it again, we would again get 13. So each time we run it, nothing will change. We always get that next number. But there is similar function with the name nextValue4. If we use this function, nextValue4, that case we would again get 13, but only the first time, because each next time we would shift our sequence by its increment. So we would get 14 and then we would get 15. So this is the same as that statement select nextValue4 sequence. So this statement is the same as this one. So these two statements are the same. And in this case, again, we would get next number, but our number will be shifted. So in that way, we can read our sequence numbers.